Latent diffusion models have become the norm in image generation because of the computational inefficiency of pixel diffusion. But can we use the structure of information in images and the diffusion process to make pixel diffusion viable again? That is the question we seek to answer in this work, Scale Space Diffusion. I'm Soumik, and this work was done with Prateksha and Abhinav. First, we try to quantify the amount of information in scale spaces versus diffusion. Information in diffusion can be quantified using the probability of the signal dominating the noise, while the information in scale spaces, that is Gaussian image pyramids, can be calculated using the normalized area of the image. Based on this, we observe that the trend in the information is surprisingly similar between scale spaces and diffusion. This brings us to the question that if small image and noisy diffusion state have the same kinds of information, that is the shape of the face but not the details, then why do we need to process these many pixels during the noisy diffusion state? This brings us to combining scale spaces and diffusion. Essentially, we want to generate from a small random image and upsample and denoise at the same time to generate an image. This should be more efficient and should even have an easier time to navigate through the search space. To achieve this, we introduce scale spaces into diffusion processes math. This is the change we make. Standard diffusion states have a signal and a noise term. We change the signal coefficient to be a linear degradation operator. As for the choice of this operator, we choose a chain of resize operators as our degradation. And the reverse diffusion process changes accordingly. If seen carefully, they're analogous equation but in multivariate. Now, architecturally, UNet is not designed for multi-resolution processing. It can only handle fixed input-output resolutions and processes using symmetric encoder-decoder pathways. But we need the model to handle change in resolution. But using all the layers for even tiny inputs is wasteful. Hence, we need an asymmetric pathway of processing. We need a more flexible network. Introducing Flexi-UNet, which dynamically activates resolution-dependent subsets of layers. Low-resolution inputs are only processed through the deeper blocks, and the resolution transitions are handled via asymmetric pathways. And in this way, we encourage setting resolution or rather information-dependent compute budgets for efficient allocation of compute. Initially, we start from a small noisy image and the model only uses the innermost block to predict the clean image, which is used to create the next state, and then it denoises it. And after a few of these, there comes the resolution changing step where the model predicts the clean image at a higher resolution. And then again, we go through resolution preserving denoising before moving to resolution increasing steps and so on. Till we generate the final image. Here are some generated results of CelebA. And the diffusion process looks like this. More interestingly, the model's clean image prediction evolves from an average face and then tries to figure out the gender and then the color of the skin, and finally the finer details like beard and hair. We see increase in efficiency with increasing final resolution and the number of levels of resolution. The inference time is sped up by a lot, and the quality is comparable at fraction of training time and compute. One could also choose a different degradation operator. Like instead of using a 2x downsampling, we could choose a gradual downsampling. So the takeaways are Why waste full compute on noisy states? In this regard, we infuse scale spaces into diffusion to get scale space diffusion, which leverages the information hierarchy in scale spaces to make pixel diffusion viable again. Thank you.